Hi, we are very fortunate to have Dr. Lily Elefteriadou, Director of UFTI at University of Florida and a Professor of Civil Engineering. So we'll hear from her today. So thank you, Lily, for accepting our invitation. So we are eager to hear from you. Thank you.
Good afternoon, and thank you for having me. It's a pleasure to present, despite the fact that we cannot travel. So my presentation today is on a project that is funded by the National Science Foundation and the Florida Department of Transportation, and it deals with optimizing traffic signal control for connected and autonomous vehicles. And my co-PIs are Carl Crane from the Mechanical Engineering Department and Sanjay Ranka from Computer Science. Before I talk about the project, just a couple of words on the Transportation Institute, and I'm showing here the website if you have questions about the type of work that we do. But we are a very interdisciplinary group with more than 100 faculty affiliates across many departments and colleges, about 35 staff. We have the research groups on autonomous vehicles, autonomous connected vehicles, data analytics, safety, human factors, sustainability, infrastructure. And we also have two groups. You may be familiar with McTrans Center, which develops transportation software, and our tech transfer group. We also are the lead university for the regional UTC STRIDE, and our focus is on congestion mitigation. So this presentation today is on the two projects that I mentioned, one by NSF and the other by FDOT, and we are toward the end of that. We are in the last year. The project expires in August, even though this last year is the transition to practice, and because of the COVID-19. We may not be able to do all the field testing that we're planning. But there's also a simulation component, and as I said, the field testing component to it. I'm listing here the project team. Some of the graduate students have already graduated. We have several new ones that have taken their place, but overall quite a large group. There's many different components to making this work from several different aspects. So I'll give you the big picture of the overall project and where we are so far. The basic idea is taking advantage of the autonomous and connected vehicle technologies, so the communication with the infrastructure, the sensors, and autonomy, to be able to optimize the way we do signal control. And the state of the art with signal control is to be demand responsive, but when you have the ability to directly communicate with vehicles and get advanced information about their arrivals, their destination, and in the case of autonomous vehicles, to be able to provide them with a recommended trajectory, that gives us a great opportunity to be able to optimize the signal control together with the movement of the vehicles. So in our project, the objectives are first to develop novel optimization algorithms that would be able to optimize jointly the autonomous vehicle trajectories and the signal control, so that we can minimize the travel time and maximize throughput. To also consider within that connected vehicles and conventional vehicles, kind of by predicting where we anticipate they would go based on acceleration, deceleration capabilities. To do that, we also developed a simulation environment for testing. And because the project also has a transition to practice component, we also developed detectors and use data fusion algorithms to be able to collect data real time in the field about the movement and the location of conventional vehicles. And the culmination of that is to implement the algorithm at an intersection in the field. And the intersection we are working with is on the UF campus. It's the Gail Lemerant Stadium road intersection, which has already all the sensors implemented, and I'll talk a little bit more about the testing that we're doing there. So what I'm going to do today, because as I said, this project has many different legs and directions. I'll just give an overview of the big picture. And in the end, I'll provide a list of publications if you have specific questions on any of those aspects. So I'll talk about the results from simulation for the autonomous vehicles, for 100% autonomous vehicles in the traffic stream. Then I'll talk about the process for optimization for mixed traffic. Then I'll talk about our simulation environment. I'll talk about the sensors and how we are dealing with that in the field, and our transition to practice work and next steps. So here's the overview of what we're accomplishing. We have information that flows from autonomous connected vehicles into our sensor fusion. We have information exchange with conventional vehicles, and then we have one-way information for conventional vehicles where we are detecting their location and we're able to track them. This information is synthesized. It's used as input into our algorithm. Our algorithm generates optimal trajectories and optimal signal control. So the optimal trajectories are being sent back to the autonomous vehicle, to the connected autonomous vehicles. They're also we're also sending optimal recommended trajectories to conventional vehicles, and we're also sending the signal control to the controller. This is kind of the same information, but in terms of the data and the flow of the data within this this concept. To be able to make this work, one of the components in the optimization is how to optimize the autonomous vehicle trajectories. So the way we're doing this is, and what I'm showing here is for a turning movement, for a left turn. We are optimizing such that at point A, we have vehicles departing at the saturation headway. And we have them also depart at the maximum possible speed so that they can make that particular movement. The figure on at the bottom shows the shape of those trajectories, and what you can see here in the stars is the saturation headways, which are the ideal departure times at the ideal speed. Let me say that this doesn't happen for all volumes. There is a time where you reach the capacity based on the saturation time headway, and beyond that, you're not going to be able to add more capacity to it. So the system is constrained by that saturation time headway. But what we're doing is we are planning the trajectories such that the vehicles are able to depart at that saturation time headway and at the maximum speed. And the reason I'm showing the turning movement is that maximum speed really depends on what movement we're talking about. Because if it's a through movement, the maximum speed would be higher than if it is a left or a right turn movement. So the first results I'm going to show are for optimization for a system with 100% autonomy. So the intersection that I'm showing here is our test intersection. The circle shows the communication range. So the assumption is that as vehicles enter that communication range, they send that information to the, that's when they start to send information and receive information from our intersection controller. So for this first set of results, for this type of intersection, the optimization process follows this graph where we are looking at optimal trajectories for lead vehicles versus optimal trajectories for following vehicles, so that the follower would follow the hypothetical optimal saturation departure curve when it can do that. In some cases, the vehicle cannot accelerate quickly enough to reach that, so we have constraints on that, and the optimization process that we used here was based on oops. Can you hear me, Charlotte?
Yes, I can hear you. Yes.
Okay, great. I got a message from Charlotte that she could not hear.
Oh.
Okay, so the objective here is to optimize, as I said, the lead vehicle and then the follower vehicle, and the in this particular case we use genetic algorithms for the optimization. Okay, and this is a graph that shows the optimization horizon scheme. So the way we are handling the optimization is we have the vehicle arrivals here in the first time period, and I hope you can see my cursor here. But we have optimization or arrival information at the first time period, which is then projected to signal timings later. So we can project what the trajectory should be together with what the signal control should be at a certain time later. And we have stages for optimization, which we then update based on new arrivals, because this graph or this type of information is what we have from each approach. And this is the optimization process where you have some initial data on the geometry of the intersection. When it's simulation, we have vehicle generation parameters that we can manipulate. So we generate the vehicles for the optimization period, and then we optimize the movement of vehicles. We use the genetic algorithms to do the optimization for each stage. Let me get to the results here. I'm going to show some comparisons in this graph, or these two graphs. I'm showing comparisons for balanced demand, meaning we have similar arrivals from all of the approaches. And the top left shows travel time versus demand, and the dark blue shows actuated control. Lighter blue shows the results from our algorithm. So what this is showing is that for lower demands in terms of vehicles per hour per approach, there isn't really much of a difference in delay between actuated control and our algorithm. When you get to the higher demands, 14, 16 vehicles per hour per approach, that's when you see most of the savings, because at that point we're able to arrange vehicles much closer together, and so they depart at the saturation headway, and we're also optimizing in such a way where we take advantage of this two-way information between vehicles and the intersection. So the delay we found in this simulation is reduced between 16.3 and 79.3 as a function of demand. Similarly, for the bottom graph shows vertically the throughput as a function of demand, and again, we get most of the benefits in terms of throughput at the higher demands. For the lower demands, it really doesn't matter a whole lot. This is same graphs, but now for unbalanced demand, so meaning the two approaches have more demand than the other two approaches. So we have a main direction and side street direction. And because we're optimizing of the way we are optimizing, it really doesn't matter whether the demand is balanced or unbalanced. We get kind of similar results and similar savings. Another thing we evaluated is the effects of the communication range. And what I'm showing here is for 4 different demand levels: 600, 1000, 1400, 1800, how the delay is improved as a function of the communication range. And I'm also showing what the expected DSRC range is, around 1500 feet. I may be a little bit optimistic, but you know, when you get to, you get most of the benefits when you are within that range. So yes, you do gain a little bit more by longer communication range, but not significant. And again, we're talking about 100% autonomy here. The results that I showed so far is for 100% autonomy, and it's also for in simulation. When we started to think about implementing this in the field, there are slightly different considerations, because in the simulation, you can start with a certain set of vehicle arrivals. Excuse me one second. So in the simulation, you can generate all the vehicles and plan it in advance. But when you're dealing with the real world, now you have to consider the movement of each vehicle and how that changes as you are doing the optimization. So the graph that I'm showing here at the top shows vehicle trajectories. This is distance versus time. And let's say that this interval here, the delta t, is the amount of time we use to collect vehicle arrivals and conduct the optimization. From the first vehicle that arrives until the last vehicle that we consider in the optimization, the first vehicle has already moved from its initial position to some position closer to the intersection. And so the trajectory that we optimize has to consider that the vehicle has already moved somewhat. It's not static as it would be in simulation. And the distance that it has covered would depend on the arrival speed primarily, and also the optimization period. So this delta t is very important, and also the slope of this of the trajectory. And so the smaller that amount is of the optimization period, the less information we have to make to do the optimization. But the longer that interval is, the closer the vehicle is going to be to the intersection, and the less flexibility we have to provide an optimal trajectory. So what we developed a graph that's shown here at the bottom that shows what are the feasible communication ranges versus the feasible speeds and the recommended intervals that can be used for this delta t. As you can see here, if that communication range is too small, and the interval delta t is too large, the vehicle will be too close to the intersection to optimize. So there are some significant field implementation related issues with this. Obviously, the longer the communication range, the more flexibility we have to develop those trajectories. Okay, I'm going to get to the second application, which is for now for mixed traffic. When you have mixed traffic, you need to maintain conventional signalization. So in this case, we have to have the yellow all red with a certain duration, and we have to follow the phasing in a more traditional way. But the concept is very similar again, and the way we are doing the optimization is we have a set of feasible phases, and then we optimize based on those. When you have autonomy, you have a lot more flexibility with the types of movements and the combinations that can be used. And this graph shows the results of with mixed traffic. Now we are looking at we're looking at different market penetrations. So the size of the bubble here shows the AV ratio. The colors show the communication range from 500 to 3,000. The first row shows average, what is it? The average travel time. The second shows delay, and I'll explain why those are a little bit different. And the bottom shows the durations of green. Each of the columns shows a different saturation headway assumption. So as expected, when you have a higher percent of AVs, you have lower delays. You were able to arrange the vehicles much closer together so that we can improve the throughput and lower the delays. Of course, as expected, the minimum saturation headway significantly affects the travel time. We're able to increase the throughput in that way. What we found is that the communication range does not significantly affect the delay beyond a certain distance. And what we also found is that with the higher flow rates, we have lower effective green. So we have more frequent switching between the phases. We did a comparison also with VISIM, and what we're finding is that again the algorithm is most effective for the higher flows and the lower saturation headways. We are finding that we have higher average effective greens because we are able to reduce the gap outs, because vehicles, their trajectories can be adjusted so that they follow at that ideal saturation headway. And these are the results. Charlotte, I'm not sure if you're seeing this. It says my screen sharing has paused.
Yeah, we are stuck on the previous slides where you're showing the flow rate, and yeah, okay.
Okay, let me see why. Not sure why this is happening, but
yeah. I think we should go to slide 21. Yeah.
Are you seeing it now?
Yes, yes, perfect.
Okay, good. So what the numbers show here is the throughput per scenario as a function of the CEV percentage, and this is for the intersection shown here on the graph. We simulated an intersection that's here in Gainesville with multiple lanes and multiple movements. And you can see here the throughput when you have, of course, at low volumes, the arrivals are equal to departures. When you get to the higher demands, you have much higher you're getting to the point where you have now congested conditions, and so your departures are lower than your arrivals. But when you have 0% autonomous connected vehicles, your throughput is 568 versus 100%, you get up to 635. And this graph shows a comparison between different scenarios, and actually we did a comparison between genetic algorithms and a new method, the minimum cost flow, and the second one had generally much better results, both in terms of throughput and travel time. Now let me talk a little bit about the simulation environment, where one of the things we're working on, and we're not there yet, is developing a logic for autonomy in the loop. So we're using the autonomous vehicle here at UF, the SIMAR lab, and we want to have that in the loop of BISIM in such a way that we bypass the sensors that the vehicle uses, but we use its logic. And the reason for that is with BISIM, in order to simulate autonomy, it's not as simple as modifying the car following, lane changing, and all that, because we don't know the way that an autonomous vehicle would function. If we are able to put that in the loop and collect information in this way, then we have a better sense of what those types of algorithms are able to do within a mixed traffic environment. So this is what we're working on, is we have for the autonomous vehicle its location and all that for every step, and it also has the ability to see within this circle. So we provide information from the micro simulation that would translate into what sensors would typically see. And again, assuming that the sensors are 100% reliable and accurate and all that. So we provide those local coordinates to the autonomous vehicle, and the autonomous vehicle decides its trajectory based on that information. We've run into some issues with synchronizing the two software packages, but we hope we'll be able to resolve that soon. What I'm going to show you here is a simulation on a freeway, because I think it helps show what the idea is with the optimization of trajectories a little bit easier to understand. And this is from a PhD dissertation, Clark Letter. One of our graduates worked on that. The top shows autonomous vehicles, the bottom conventional. And what we're doing is we're moving the autonomous vehicles such that we are achieving as close to the saturation headways or minimum headways as possible across all lanes. So you can see that with the autonomous vehicles, you're still able to maintain undersaturated flow, but for conventional vehicles, you start to see more queues develop on the right side. We're developing a visualization tool so that you're able to see that for an intersection as well. We're almost there with that. The last part I wanted to talk about is the transition to practice, which is really the hard part, because a lot of different things have to come together for us to be able to work to do this effectively. So the idea is that we would implement the algorithm I shared with you first in a closed course, and then in a real intersection, and we would be able to do an evaluation of before and after conditions. For our initial testing, we did some work at the facility that the FDOT has, the Florida Department of Transportation, at their laboratory in Tallahassee. It's the It's called the TERL, Traffic Engineering and Research Lab. And you see the picture here at the bottom with the intersection, that closed course intersection with the autonomous vehicle. And so we brought our equipment there and several vehicles, and we did extensive testing to connect our computer to the controller that's there. Tested the communications, tested the communication to the vehicles, and then to the controller, and also tested the video. So I'm going to show you a video from that test. Oops. Okay. Okay. Let me see if I can hold on a second. Okay, hopefully you can see it. So what I'm going to show you is images from a drone we had at the lab, and we had 6 or 8 vehicles. Conventional, we had some connected vehicles, and we also had some. Yeah, so what I'm showing here is vehicles approaching the intersection, and the idea was that the signal would turn green as it was approaching, as the vehicle was approaching the signal. At that time, we also had developed a very rudimentary app, so that if the vehicle was conventional, we would be able to send recommendations to the driver on the optimal speed that the vehicle should follow in order to clear the green. We've been doing some more experiments on that, and hopefully for our next testing out in the field, we'll be able to have a little bit better information. It took us a couple of days to figure out all the connections. There's a lot of different details that point to this type of testing. Yeah, we spent pretty much 2 full days trying to get everything to communicate. And one of the important elements there was the communication from our computer to the signal control. So that took some doing. I'm gonna here and continue with the next one. This is kind of the view of that intersection, and one of the constraints also was that one of the approaches is at an angle, and so you have to have much lower speeds than what you might have in an intersection in the field. But given what our objective was to make sure that all the equipment was working properly and the communications were in place, it really didn't matter to us that much. Where we are now is we have a permission from FDOT to test at the signalized intersection of Gay Lemon and Stadium on the UF campus. We were gearing up to do that earlier in the spring, and we've had to push that, which we just got permission to test the first week of June, because everybody's going to be in their own vehicle, so it will be all social distancing and all that. So we hope to have more results then. Here's the intersection. I'm going to show you here one of the approaches to that intersection in the field, and I'm just going to show you how the trajectory optimization works. The little dots here represent the optimal trajectory, and what you see here from the green is the actual trajectory. In this particular case, these are conventional vehicles, but we were just testing how this would work and testing the sensor fusion, which is based on LiDAR, radar and DSRC and video. Let me continue that. One of the other components we're working on is the incorporating pedestrians. And so at this point, we have developed in the simulation an equivalent pedestrian push button so that we can provide a call into the simulation. So we've been testing this for within the overall optimization so that we're able to implement at the intersection. The way we're handling pedestrians is as the equivalent pre-timed phase. So whenever there is a call, we provide that particular phase without a variable time. Based on the experiments and the work we've done so far, I've summarized here some of the risks and challenges. The major one is the sensor detection and accuracy. What we're finding is that there is no single method that has enough accuracy so that we can rely on optimization on that, and that's where the data fusion has become essential. So we're using multiple different sensors to get an accurate count and to develop trajectories. This may not be the most realistic to do at just any intersection. This is all, at the testing phase and experimentation. So I wouldn't say that this is ready for prime time, because it may be too expensive to have all these different sensors, in a large network. We ended up changing the algorithm so that with driver behavior for conventional vehicles, we would be able to modify the algorithm or the optimization settings. So we optimize more frequently to adjust for movement from conventional vehicles that does not follow what we expect is going to happen. We also, in our modifications, we looked at congestion effects, and so having this optimization more frequently allows us to consider oversaturated cycles where you have vehicles stop more than once, and so it allows us to keep track. As I said, we're working on the pedestrians right now, and this was part of what the FDOT project was about, to be able to consider the presence of pedestrians. The way we're handling communication failures is we have the algorithm revert to pre-timed control, but later on we could modify that so that it could revert to existing loop detector so that it would work as an actuated controller. Where we are right now is testing the Python, the Python code, which is what we've developed this on, for several different scenarios, and we're evaluating how the trajectories look, and that's where the visualization tool we're finishing is helping us to do just that. This has been very useful to do. We're doing more field testing for the fusion for multiple inputs. We plan to do some more or some testing for pedestrians, even though we are kind of simplifying it, as I said, so that for pedestrian phases we have pre-timed phasing. And we plan to do continue with the testing through the summer. The NSF project ends in September. And just some closing words on iStreet, because this project is part of the iStreet, which is the real-world transportation testbed in Gainesville. It's in collaboration with the University of Florida and the Florida Department of Transportation and the city of Gainesville. And we couldn't be doing all this experimentation for this project without the city of Gainesville assistance, because they're the ones that are giving us access to the cabinets. They've helped us with installation of the different equipment, and they're doing the same across other research projects related to I Street. And I'm providing here the website if you want more information on I Street projects. We have several different projects. The map that's shown here shows where the instrumentation is. The purple is I-75, and then the red is arterials. The green is the UF campus. And I have a list of publications that are out so far. We're working on several more. As I said, there's several different components to this. Some relates to the fusion, some relates to the full autonomy, some relates to the field testing. So several different aspects to this. And with that, I'm going to turn it over to Ronnie, Charlotte. I'm not sure who's going to answer questions. Thank you.
Yes, thank you very much. If you have any questions, feel free to put them in the chat, or you could raise your hand and just let us know.
Yeah, I have a question for Lily. So Lily, so you mentioned that you used so you simulated VSIM and another software package. So you mentioned you used two software packages. So what is the other one? So yeah.
The SIMAR, it's the SIMAR lab, which is the autonomy logic, which is the Carl Crane's group has developed, okay. And it's basically the brains of their autonomous vehicle.
Okay.
So it's yeah. One of the students, Patrick Neal, is now working with software called AutoWare.
Yes.
So this is another option that he's looking into.
Right. Okay. Yeah. So we have used pre-scan VBot to connect with other simulation tools.
Yeah. Were you able to work to make the simulation work in the loop?
Yes. Yes, we were.
With what micro simulator did you use?
We used Sumo.
Oh, and Sumo. Yeah. And it worked?
Yeah, it worked. Yes.
Oh, good to know. That's good.
Hey, Lily. Hello, can you hear me?
Yes, hello.
Yes, this is Hongla from University of Nevada, Reno again. Yeah, thank you very much for the talk. It's very useful. I watched the video, a very nice video about the multiple autonomous vehicles. There are two video scenarios, one with autonomous vehicle and the other one with normal vehicles. So did you have deep learning or reinforcement learning training for those vehicles to go in these scenarios? Did you get my question? Do you have reinforcement learning or deep learning training for the autonomous vehicle?
Yeah, I'm not familiar with the autonomous vehicle logic. This is the mechanical engineering group. This is Carl Crane's group, and yeah, they're the ones handling that. They have they developed their own autonomy. I'm not sure exactly how and what they use, but as I said, they're looking at additional options right now with AutoWare. That's as far as my knowledge goes on this.
Okay, all right, thank you. I think I kind of saw this one, these videos in the robotic conference in IROS 2019, I think. Maybe one of the students presented it. I just wonder, if...
Say that again?
I saw this video in the robotic conference. I think maybe the students was in the conference present this video. So I just wonder if the deep learning have been used for training the vehicle.
Yeah, Carl Crane would be the one to answer that.
Okay, okay, thank you, Nini.
We have two questions in the chat. The first question is from Zadid, and he is asking if there was a specific reason to use the genetic algorithm for optimization.
We were trying different approaches, and this was just one of the options. In one of the earliest papers, we had one approach, we had two movements, basically in two phases. And in that case, we did enumeration. And this was the first paper. When you have a more complicated intersection and multiple lanes and movements and so on, you cannot do full enumeration. We tried the genetic algorithms. It worked, but it's not as good as the minimum cost flow, which was the latest one that we used, which is the paper is now under review, actually.
Okay, and then I think as kind of a follow-up to that, then Sabir Selek has asked, just for clarification, with the genetic algorithm, can it run on real time as it is an iterative or iterative approach?
Yeah, you know, we are not doing genetic algorithms for the real time. This was one of the initial ones with full autonomy, 100% autonomy that we tried, and we've only tried it in simulation. And because the results were not as good as the minimum cost flow, we ended up not bothering to translate that into real time. So yeah, it's true, it may not work as well in real time. We didn't try it because it didn't work as well as the minimum cost flow approach.
Okay. We have a question about sensor fusion. If you could please elaborate on what types of sensor fusion algorithms were used.
Yeah, sure. Again, and so this is the work from the computer science group. But what we did was, first it was important to detect conventional vehicles. In order to detect conventional vehicles, you need radar, video, and when you do that, you are not sure which ones are autonomous and connected and which ones are conventional. So the first part was you have to see which ones actually provide you DSRC and which ones just do not, and so you can differentiate between the two. The second is that the video can provide you better information close by versus radar can provide more information further away. So what the fusion does is it takes advantage of the benefits of each approach so that you can use the best information depending on which area you're looking at. And so we right now use DSRC, radar, and video. And the idea is that eventually we also want to use LiDAR. And we've tried some LiDAR experiments, but the results with the LiDAR are, for what we're trying to do, are not as good. So I don't know if we will be able to use the LiDAR in the end. So we use the other three.
Okay. And we have another set of questions. How do you define the horizon of optimization, like the interval of optimization?
Yeah, as I showed earlier, the interval is sensitive to the communication range and the approach speeds. So you cannot use too short of an interval or too long of an interval, depending on the geometry and the communication range. So we've done some trial and error, and I don't remember what we have right now for the intersection. But another question related to another issue related to this horizon of the optimization is, when do you stop providing an optimal trajectory? How close should the vehicle be to the stop bar to let it go with where it is. And so we've done some sensitivity analysis on both the horizon for the optimization and when do you stop providing optimal trajectories.
And then there was an additional question with that, with how was your turning movement ratio left/through? Do you think it will affect the performance of your algorithm?
It would affect it in the sense that you are lowering the speeds for certain movements. We haven't done extensive experiments playing with that, but I would say that the results would follow what your conventional intersection or an intersection operating with conventional vehicles would do, because you would have reduced capacity because you have reduced speed and so on.
Okay. All right. Are there any more questions? Looks like that's all we have in our chat. Well, we certainly appreciate your time. And then, as with all of our webinars, we will post this video up on our YouTube and on our website. So thank you again. We really enjoyed your chat.
Thank you very much. Thank you for the invite.
Thank you very much, Lily. Thank you for the organizers. Thank you.
All right. Take care.
Take care. Thank you.
Bye-bye.
Bye.
Bye-bye.